This is Jayden Rivers attacking the Tcache in GLibc 2.32. So let's please welcome Jayden to the stage.
Jayden Rivers. I'm studying computer science while working at InfoSect. And in general, I'm interested in binary exploitation and software engineering. In this talk, we're going to cover allocating memory, dynamic memory management. In particular, we'll look at the attacker's perspective on exploiting the memory allocator, Malloc. And within Malloc, we'll look at exploiting the Tcache. And lastly, we'll look at bypassing safe linking, which is a new mitigation in GLibc 2.32 with the technique known as Tcache list head poisoning. So firstly, what's allocating memory about? There are three main ways of managing program memory. The first is automatically, and these are managed via a kind of a stack-like data structure, basically because a stack is last in, first out. So it's good for nested function calls. The duration of a stack region or frame, or the local variables therein, is dependent on the lifetime of the function which manages it. We also have dynamically allocated memory, and the duration of a dynamically allocated region is basically constrained by the programmer's choices, as well as how the memory allocator is actually designed and implemented. These regions can exist beyond the lifetime of any single function, and it's the responsibility of the client to allocate and deallocate correctly. So as opposed to automatically managed memory, these are manually managed memory. We lastly have statically allocated region, and these are basically, they're defined in the global context, so they exist for the duration of the process. The distinction, I think, between automatic, dynamic, and static is the duration and scope for which a region is well defined. But we might also be able to access regions outside of their intended duration, scope, or their linear boundary in the virtual address space. And I think this is kind of the basis for memory use errors. So automatic memory management, I think, is pretty easy. You call a function from another function, their arguments will get passed, enough room for local variables is prepared, and a reference to the next instruction for the CPU to carry out when we exit that function context will be kept either on the stack frame or in a register, depending on what architecture you're using. So let's look at dynamic memory management in particular. Dynamic memory management is more difficult, I think, and we'll look at PT Malloc, which is part of GNU-libc. Malloc is what they call a heap-style memory allocator. And there are other types of allocation mechanisms such as slab and buddy. Interestingly, the FreeBSD user space allocator, I think Malloc employs both of these styles. But we're only going to focus on Malloc as it appears and used in GNU Linux systems. So a heap-style memory allocator has a range of possible sizes of memory which the user can request from Malloc. And these regions will all be stored together in a larger region of memory called the heap. And you can see here the virtual address mapping of the heap. Each new allocation will sit at a higher address in the heap. However, as we will see, not every region returned by Malloc is necessarily new, as deallocated regions might be recycled, basically for the sake of efficiency. So the idea is that we don't want to keep cutting up the virtual address space when we can just reuse already cut out chunks. This reduces fragmentation in the heap and speeds things up a bit. The memory regions which the client can request from Malloc are called chunks, and they're kind of the fundamental unit or atom of Malloc. There are two perspectives and two states which relate to each chunk. To the client, a chunk will appear as a region of memory which can be read from and written to. To Malloc, who's the server, I guess, a chunk appears as management data plus the user data portion. So a chunk can be in an allocated state, as you can see above, or a freed state, as you can see below. And these two states define the metadata associated with each chunk, or basically how Malloc will interpret that metadata. Just like in stack memory, there's both metadata and data. But with the stack, we have metadata which is directly related to control flow, for example, like storing a return address. Here it's a little bit further removed. So let's just go back to basics and request two chunks of size 10, which get rounded up to hex 20, 32. You can see that in memory. But where's that metadata actually stored? So if we look at the memory, which just precedes each chunk, we can see a size field. So that's that hex 20 with a 1-bit flag, which we don't really need to get into. Here, I just used GLibc, which is awesome, to view some other metadata, which is related to the chunk which A points to. And as you'll notice, those two perspectives, so we can see the chunk size, which is what Malloc thinks the chunk is, and the usable size, which is what us, the user, will actually interact with. So let's go to the second state now, from that allocated state to the freed state. So we'll free A and B. And as you can see, there's a pointer to A at the first bytes of B, the first D word of B. And the reason for these pointers is that when chunks are freed, they're going to be linked into lists among other freed chunks, at least in the Malloc implementation. These chunks can then be recycled in future requests made by the client. In turn, the lists are grouped together in larger sets of lists called bins. These bins are the small bin, the large bin, the fast bin, and the unsorted bin. And they basically correspond to different size ranges of chunks. The unsorted bin also performs a special staging role, which we don't need to worry about. Then there's the per thread cache for each thread of execution. And the Tcache has its own set of free lists. So it's kind of like a per thread bin in a way. The Tcache has these dimensions. So they're configurable, by the way. Chunks have to be in the range of hex 20 to hex 408. The number of lists is 64, where there's a maximum of 7 chunks linked into any single list at a time. And also the chunks are singly linked, so they only have forward pointers, really. The Tcache exists because it wants to solve an additional problem compared to the other free lists, the other bins. To understand what this problem is, I'm now going to mention the other units of Malloc. So we've already seen chunks, but what else is there? So in some order of generality or containment, we have thread management, which obviously extends beyond Malloc itself. But within Malloc, we have arenas. Below that, we have heaps, and then chunks at the most fundamental. So a chunk will belong to a heap to an arena, and an arena to a thread, but only if said thread has locked the arena for itself. And this basically implies that threads can access multiple arenas over the duration of the process, but that an arena can only be accessed by one thread at any time. So here's a kind of gross representation of thread 1 gaining exclusive access to the arena and all its chunks. And you can kind of see the problem here, that if thread 2 has to wait long, then it might kind of counteract or negate the power of Malloc's free list optimization. Like, in the end, what's the point if we can't access those free chunks? Arenas serve as a structure for storing the lists of free chunks. They also have pointers to other arenas and other metadata, such as where the top chunk is in memory, basically where allocations will be serviced from in the future. So some of the fields present in an arena, as you can see here, and most interestingly for us is that top field there, and also the fast bin and bins. The problem relates to the contention between threads for control over a single region of memory and the data therein. It's a general problem, and in heavily multi-threaded applications, it can become pretty inefficient to lock and wait at certain scales. For Malloc, the solution is the established means of thread local storage. And basically, this is data which belongs to each thread and transcends the regions of memory over which multiple threads contend. So thread 1 doesn't need to worry about thread 2 trying to access its thread local storage. There's a lot more in Malloc which is not really relevant for our discussion today, but hopefully we have a general grasp on the notions of data and metadata as they're used in chunks, the units of Malloc, and also the justification or the reason behind the Tcache and the problem that it aims to solve. So what about the attacker's perspective on Malloc? Exploitation of Malloc does have quite a long history, like 20, 25 years, I think, but a lot of the techniques are no longer really possible in the latest versions of Malloc. The first notable technique, I think, in heap exploitation was created by Solar Designer, and this was the unlinking style attack. Essentially what we do here is we will overwrite the value at some location in memory by having Malloc consolidate already freed chunks. The consolidation mechanism is what they call unlinking, and one aspect of it can allow an attacker to gain a right while where primitive. And basically, this is done by targeting the pointers of free chunks in one of those linked lists. So before explaining this further, it's good to just see a kind of abstract representation of a doubly linked list. So, just basics like node 1 points to node 2, node 2 to node 3, and they also have backward or previous pointers as well. So consolidation, in order to consolidate node 1 and node 2, we would update the size of node 1 to consume node 2. So the node 1 plus node 2 would basically be treated as one block. And then to get rid of node 2 from the doubly linked list, we would unlink node 2, and then we'd leave the list looking kind of like this. So the macro to achieve this list unlinking mechanism in previous versions of glibc was what we can see here. And to explain it a bit, let's just say that P is a chunk, which we want to have consume the chunk ahead of it. So we'll set back from P to the address of some shellcode or the first link in our ROP chain. And then forward from P to the address of a function pointer or hook, and we also have to minus for a 12 bytes struct offset. And then after that, back from FD is going to be set from back from P, which is the address of our shellcode. So essentially, it's that write what where thing where we're going to be able to write the address of our shellcode to a function pointer. In a stack overflow, contrasted with this, we often want to overwrite the instruction pointer which is saved on a stack frame. But here we are further removed from code execution. All we're really doing is linking and unlinking a specially crafted piece of data into a linked list data structure. Our machines need to refer to both the code and the data to run, but often data is used to direct code. For example, storing function pointers. These pointers, they're data, but they can also be dereferenced in order to invoke the function that they're pointing, like function pointers. Overriding this data, we can alter execution. Unlinking has been followed by the House of Star series, so these also target metadata. It might be in the House of Force, which targets the available size of Malloc chunks, allowing an attacker to allocate a chunk which overlaps a function hook or the address of a function pointer in the global offset table. Or it might be in the House of Spirit, which frees a fake chunk, targeting the list links so that Malloc returns a pointer into sensitive data. What about exploiting the Tcache in particular? So for a bit of history, the Tcache was introduced in GLibc 2.26, and at that time it had basically no security checks. Many of the older freelist-based attacks were reintroduced in the Tcache. And though it operates differently, the kind of general idea is that if we're given the misuse of a deallocation mechanism, such as through a use after free or a double free condition, then the attacker might be able to get Malloc to return a pointer to an arbitrary address. It's also important to note that Tcache lists are singly linked. So we saw the representation of a doubly linked list before, but the nodes in a Tcache or the entries in a Tcache will only have forward pointers. So let's look at the abstract rep of a double free. Recall that a free chunk is going to be linked into one of those Malloc management kind of lists. Freeing it twice, we'll link the same chunk twice. And so we'll produce this kind of cyclic linked list. If we then request a chunk so we can get back A, then the list is still going to look like this. Now we'll be able to write to this same chunk while it's in the Tcache. And essentially what we can do here is write the address of a target in memory to the foremost bytes of the A chunk, such that the linked list will now look like this. So we've kind of implicated the target address within one of Malloc's own free lists. And a use after free is extremely similar. Basically, we'll have this. And then we write to the forward field of A, and we have this. And this is a write after free kind of thing. So more concretely, so that we don't have to keep looking at those diagrams, starting in GLibc 2.27, a double free of the region of memory pointed at by A. So as you can see here, once we free A or double free A, it's going to have a forward pointer back to itself. And that's the same thing as the linked list cycle which we saw previously, but it's not really that interesting just like this. But if we take this, we have a variable called overwrite me, and this is obviously just a contrived example, but imagine that it's a kind of arbitrary address in memory which relates to control flow somehow. then we'll be able to double free A, get back one of those A's, write to the forward pointer of it, and then get back the remaining reference to A, and then lastly we'll be able to write through D to the target address. So as you can see here, we'll just overwrite that. So a use after free condition, as contrasted with double free, can allow us to overwrite the forward pointer more directly. And it's not really that interesting to just do this, where we've written a bunch of A's to the forward field. But if we have a look here, we freed A, and then at 1, we've done a use after free. And then we've been able to get back our target address through the C pointer, and so we have kind of an arbitrary write. So what are some mitigations for this kind of thing? Firstly is Tcache count checking. Basically, the idea is that we can't have Malloc return more chunks than were legitimately linked into the free lists, so that the add and remove operations have to be balanced. But what we can do is we'll maintain the Tcache count between calls. So here we freed an extra chunk to set the count at the TC index to 1, and then we freed another chunk, and we launched our use after free attack again. And another mitigation is to mark free chunks with a key field. And this is even harder to bypass, but basically there are a few ways. One way is to overwrite the key field, as detailed by Silvio in this particular article. The mitigation marks chunks which are freed into the Tcache, basically by setting a key field of a Tcache node. So you can see key from E will be equal to that Tcache thing. And we don't know what that is yet, but it will come back later. When we attempt to free one of those already freed chunks into a Tcache list, Malloc will check the key field and it will stop us. So we'll enter that block up there, and then we'll do a list traversal, and eventually it's kind of guaranteed if we've done a double free that temp will be equal to E, and then we'll abort out. So how can we kind of get around this? Essentially, we can free a chunk and then overwrite the key field to ensure that the previous check fails. And here's a demonstration of the technique from the article that I mentioned earlier. So we'll free P, and then we can overwrite key from E, and we'll be able to free P again. Another way to bypass the key check is to confuse Malloc as to which list to actually check for a double free condition. And we can achieve this by toggling the size of an adjacent chunk. So the idea is that if we can change an adjacent chunk's size metadata, then we can get the same chunk placed on different lists. So while we do fail the first check and we enter this block here, we can ensure that Malloc can't find our already freed chunks because it'll be traversing or searching along the wrong list, right? So temp will never be E, even though the key from E is equal to the Tcache. And in this example, we just repeatedly toggle the size of an adjacent chunk, which we know is going to be freed in the future. And then we created cycles in the linked list, and we retrieved our target address from a bin whose count is greater than 0. So, safe linking. This is really hard to bypass, in my opinion. The constraints are harsh, and generally you need an information link in order to demangle pointers. But if we're given the right circumstances, we can bypass it by attacking the Tcache list heads directly. So, safe linking. Safe linking, for a bit of background, was introduced by Checkpoint Research, in particular by their researcher Libsy. The idea, as detailed in CPR's article, is basically to make use of ASLR to sign or mangle the list's pointers. Eyal refers to the GLibc unsafe unlinking mitigation as inspiration for this mitigation. And basically, this is because the doubly linked lists have already been protected from unlinking, from the unlinking style attack that I mentioned earlier, the one that was designed by Solar Designer. But mitigations over unsafe linking or unlinking in the singly linked lists, such as those in the Tcache, have generally remained bypassable, as we've seen. Safe linking is able to mask and unmask forward pointers. With unlinking operations over the lists, the forward pointers become mangled and then demangled. From the original blog post, we can see this kind of representation of the bitwise ops, which mangle our pointers. And we'll see that as code in a sec. So the idea is that if they are legit forward pointers, and they've gone through the legitimate process of linking by, we passed them to free and they've been put on the Tcache in a legit way, then the process of demangling the pointers is going to be reversed and we'll get out the original pointer. But if the pointer has not gone through the legit process, it's going to become mangled and bad for us, it will not be dereferenceable, probably resulting in a seg fault or maybe an abort. So the first piece of relevant code we're going to look at is in Malloc's Tcache get function. So here, we just get the current head of the list, and then we set a new head as kind of a simple list remove operation. But if you notice the macro there, reveal pointer, there's a slight difference. So compare that with Malloc of GLibc 2.31, and that was the version just prior to this mitigation. So as you can see, there's no reveal pointer applied to the next node from the head of the list. And this is actually kind of stock standard removal from the singly linked lists. And to visualize the difference, let's just say that we've got into here with our exploit. So the target address will now be part of our linked list. Eventually, we'll be able to get it back. But the pointer from the Tcache root node to A, while it's legitimate, the pointer from A into our target address is illegitimate, right? So we've freed A properly, but the target address is only kind of referenced by A. It hasn't been properly freed and added to the Tcache list in a legit way. So now we get Malloc to return A to us, and what will happen? Ideally, the target address is now going to be at the head of the list, and so on the next call to Malloc, we'd be able to get our arbitrary pointer to somewhere nice in memory. But looking at the code, we see that first E is set to the current head, which is A, and then the pointer in the Tcache root node is not actually set to the next node from E, which would be our target address, right? Instead, it's going to be set to the results of reveal pointer given the next node from E. And this is kind of where it all goes wrong. So instead of what we had before, we have the Tcache root node pointing into the result of reveal pointer, which expands to protect pointer, and that takes the position of the pointer in memory, so kind of using ASLR in order to mangle it, and the pointer itself, and then it performs the shift and XOR operations. If the pointer was not previously mangled, then demangling is not going to produce the original pointer. Instead, we will just get a mangled version of the pointer we wrote to the FD field, the forward field of our target chunk. So with our view into memory, we start with writing our target address. So that's, as you can see in blue, that's A, and then the target address is that yellow address there. And then we'll get back our first chunk. So notice the mangled pointer there. That's not the same, that's not our target address anymore. And then when we try to get this pointer returned, because it's not 16-byte aligned, there's going to be an abort raised, and we won't be able to get further than this. So this basically happens because when the Tcache get function is called again, it's going to attempt to access next from E. And this can either result in abort, which is the result of some alignment validation on the chunks in the Tcache, or it will just be a plain seg fault, since E might not even be a valid address. It might have been mangled so intensely. The way to have a pointer demangled rather than mangled in this process is basically to perform a protect pointer before a reveal pointer. And this kind of abstracts into like a Tcache put before a Tcache get. So from the perspective of a user, that would mean having a pointer legitimately linked via free, rather than through being overridden with a use after free or a double free bug. In the Tcache put function, we can see the list add operation performing some pointer signing. So that's that protect pointer before reveal pointer. And here what we do is we'll set a new head in a legit way so that a subsequent Tcache get will be able to reverse this process and we'll get back our original pointer. Safe linking, in my opinion, is ingeniously simple and it only has a minor performance impact. So in CPR's threat model, an attacker has to have the ability to leak heap addresses And these can then be used to properly demangle the forward pointers, hopefully resulting in the original primitive. However, something that I noticed here was that the Tcache put mangling occurs only when a new head is set in the Tcache list. And this kind of got me thinking that if we can control the list head more directly, then no demangling would be performed on the target address, as our target address would never actually be at next from E. So to visualize it, instead of this, we're just going to start with this, and we don't need that third party kind of A. But how could this work? The Tcache root node is not meant to be part of our own free chunk metadata. And we shouldn't be able to just access it or write to the head of the list which it refers to. To give a bit more context, the list head sits at an index in an array of pointers. And this array is part of an internal Malloc management structure called the Tcache per thread struct. Luckily for us, Malloc also inlines this Tcache per thread struct in the heap. So as evidence of this, in the Tcache init function, a hex 290 sized heap allocation is made. And this is the memory for the Tcache management structure. So here it is, and that's overlaid as the first chunk in our heap. So we can see the array of pointers, entries. We can also see those counts there. So what can we actually do with this information in order to attack safe linking? We can do Tcache list head poisoning. But before we get started in this section, I think it's worth mentioning that with the write what where primitive, which is what we're kind of aiming for, we need to target data which has some effect on control flow. We might want to target application-specific function pointers, or as is in the case in this section, we can target the memory allocator hooks, in particular the free hook. So a hook in this context, just to give a bit of a definition, is just an address which is checked prior to the execution of one of Malloc's internal functions. And if the address holds a non-null value, then Malloc is going to assume the value to be the address of another function to be executed in place of this default function. So here we can see the code in malloc.c, and this basically reads from the free hook to see if Malloc should call a custom free implementation. So you can see there the atomic's forced read, and then the function pointer is checked to make sure it's not null, and then it will be dev-referenced and called. So the idea is that if we can get Malloc to return a pointer to a hook, and we subsequently write to it, then the next time the corresponding function is called, our own code will be executed in place of it. And we won't focus on this, but usually you'd want the address of the first link in your ROP chain to be the new hook, or maybe the address of system or something. So now that we have a target in mind, for the remainder of this section, I'm going to detail a few variants of the Tcache list head poisoning attack with some hypothetical bugs. So attacking the Tcache list heads could be achieved with a negative offset write, which might be caused by a user-controlled index or a signage to overflow, or decrementing an index or like a cursor pointer below 0. And it could also be caused by a use after free, given some constraints. So with a user-controlled index, let's just say that we have a function which performs a set operation on an array. If it only checks the requested index against the upper boundary of the buffer, then it might be possible to write at a negative offset. And here that would mean that where is a negative integer. So here we wrote directly to the Tcache list head with a negative offset from the beginning of a heap buffer. And then we overwrote a hook and we got code execution. So essentially when free B is called, it'll be calling hook override instead. So where exactly are we writing to with this negative offset? We can see the hex 290 Tcache management struct in our heap memory. What we have done essentially is we've written the address of our target free hook to the list head corresponding to the free chunks of size hex 3A0. And to show it with some really nice colors, we have our previous representation and also the memory view. So the free hook is at that list head. So code which doesn't perform lower bound checks on signed integer indices does exist in the real world, but looking at previous CVEs, it seems pretty rare. And I think this is mainly because the accepted practice is to use unsigned data types for variables which might end up being users' indices, and also generally to attempt to limit user-controllable indices. So an index overflow. What about overflowing a signed integer, which is subsequently used as an array index? So let's just take a custom stack implementation and say that we store the top of the stack as a signed integer and we begin repeatedly pushing values. If we increment the index beyond its data type's range, then it will wrap around to become negative. So here's just a quick refresher on what a signed integer overflow is. If we keep incrementing a signed variable, and I just used a chart just so it fit on the screen, then at the limit of its data type's range, it's going to become negative. And below is the result of incrementing a chart type, which has the smallest range in C. Application logic permitting, this could allow us to write to a negative offset from the beginning of the buffer. And so we'll be able to write our target address to a Tcache list head. So let's look at the potentially buggy situation. So here, a check will be performed to ensure that the stack hasn't overflowed beyond its upper boundary, and this check kind of allows an off by one already. But more importantly, if the top from stack variable wraps around to become negative, then we will be able to write below the lower boundary of the buffer, hopefully up into a Tcache list head. So in the SEI Cert C coding standard, we find this related quote, that the sanitization of signed integers with respect to an array index operation must restrict the range of that integer to numbers between 0 and the size of the array minus 1. I've seen a few examples of signed integers uses both iterative variables in for loops as well as array indices within those. So what if we decremented our index or maybe like our cursor pointer below the lower boundary? Sometimes it's useful to pass input data in reverse, starting at the upper boundary of the buffer and working our way back down. So for example, say that we read a binary file in reverse and we miscalculate the last index of the buffer, which we are reading into. We'll just continue to decrement buff pointer below the address of index 0. And this could allow us to write into the Tcache management struct again. And I'm just kind of showing different potentially buggy situations, just cases to show the problem with putting the Tcache management struct in the same heap. So some questions which we have to consider with these already seen variations are, how far away will the Tcache management struct be from the chunk that we control? And what other malloc metadata will we corrupt when writing below our chunk in memory? So looking back to the threat model of safe linking, they say that the mitigation is aimed at stopping attackers who have a controlled linear buffer underflow or overflow over a heap buffer, or a relative arbitrary write over a heap buffer. So we can say that this does already constitute an attack vector, which safe linking is modeled on, even if the conditions are harsh and semi-unrealistic. But what other variants of list head poisoning are there? So if we look back to the malloc.c source, we can see the key field from the mitigation that I mentioned before. And notice how it's a pointer. The key field actually holds the address of that Tcache management object. So in the Tcache init and Tcache put functions, we can see where that happens. So the Tcache will be that global pointer, and then key from E will be set to it. And essentially, that key field mitigation, which we saw earlier, actually initializes a pointer to the Tcache management structure in every chunk linked into the Tcache lists. And the fact that it's a pointer rather than just some random hash or an XORed pointer or even a protected pointer within safe linking's own logic, that means that we can dereference it directly. So if we can pass this pointer to free, then we might be able to place the Tcache management struct on a Tcache list as if it was freed as part of those Tcache list freed chunks. And this ensures that it's legitimately pointer protected so that we can request it from malloc in the future. Additionally, the Tcache management struct is already a legit chunk, so freeing it won't actually be a problem in terms of the metadata validation routines that malloc will run. So in this example, we freed a pointer field after we freed its encapsulating object. And this is just a kind of really silly binary tree, but the idea is that the key from E will be at right from root after we free the encapsulating object. So here we can see that the Tcache management struct was linked into one of its own lists, specifically the hex 290 list, as you can see there. And I'll just point out that the 5010, that's our Tcache management struct. So from there, we can get it returned by Malloc, and this would allow us to write to the list heads in the future. The technique does have 3 stages before it can be used to the same effect as the historical Tcache attacks, and there is a size constraint on getting the Tcache struct returned. So let's now look at writing with a useAfterFree to a struct field. In this example, we wrote to the right child of the root node, and this incidentally wrote our target address to the Tcache list head at that hex 80 offset from the beginning of the Tcache per thread struct. And with our view into memory, we can confirm that the write was successful. So free hook will now be the head of the hex 20 Tcache list. And of course, I just put this in for completeness, but the attack is also possible in applications written in C++, because as before, the second pointer is set to the Tcache key. But this is kind of obvious. So here are a few examples of dynamically allocated structs with pointers which would be in the correct position and of the right size. And the reason why I included the last slide is not to pretend that having a pointer at a particular offset in the struct is necessarily a bug, but I wanted to emphasize that it does seem very common for people to store pointers at the same place. And the worry, I think, with this almost default way of approaching dynamic data structures is that Malloc has no facilities to autonomously distinguish between what metadata and data is. They're essentially the same thing. And given this fact, I think programmers might want to organize their dynamic data in a way which makes the boundary between Malloc's metadata and our own data better defined. I think this is kind of comparable to how we don't want code and data to get mixed up, hence non-executable mappings. In the same way, we want to limit the potential for metadata to be interpreted as data and vice versa. But this is just my opinion. Regardless, there's still something kind of unsatisfying about this pointer position constraint. So can we loosen it a bit? Using a House of Spirit style attack, we can construct a chunk contained within the larger chunk. And we do this to override a pointer at whatever 16-byte aligned offset we want. So we've reduced the constraint from necessarily an 8-byte offset from the beginning of the Tcache per thread struct to a 16-byte aligned offset from wherever in the Tcache per thread struct. So here we used the House of Spirit, which is kind of an established technique, to control a pointer which is passed free. And with some influence over the data inside the chunk, we were able to pass Malloc security checks. So you could imagine doing a kind of like partial override of a pointer in order to achieve this. So with our view into memory again, we can see that we overwrote the pass pointer with the address of the Tcache management struct. And note how the pass pointer is not at that 8-byte offset anymore. After that, we freed it, and we achieved the same thing as before. So we've kind of loosened the constraints a little bit. With heap exploitation today, you usually need to leak an address from Libsy in order to defeat ASLR by calculating offsets from the Libsy base address. For example, how do we know which address to actually write to the free hook? One answer is to write the address of the system function to the hook, or maybe like a ROP gadget or something. We can extend the technique shown here to get a Libsy leak, or maybe some other primitive on our way to code execution. So recall the Tcache count checking mitigation that I mentioned earlier. There's a configurable limit on the number of chunks which are allowed in any one list at a time. By default, this number is 7. So what happens when we try to link up the 8th chunk? Then the below check will fail. So if this chunk doesn't go into one of those Tcache lists, it's going to go into a list from one of those bins that I mentioned earlier. For this example, we target the unsorted bin. The unsorted bin, The unsorted bin has a circular doubly linked list. So if a chunk is linked into the unsorted bin, then it's going to be initialized with 2 pointers rather than just one. One to the previous chunk and another to the next chunk. So then say that we are dealing with the earliest added chunk or the least recently added chunk. While the BK field points to our second chunk, the FD field will always point to an address, which we can kind of guess is the unsorted bin root node. So what happens if instead of only linking the Tcache management struct onto one of its own free lists, we also linked it into the unsorted bin? So with some heap grooming to ensure that the chunk validation passes, we can write the address of the unsorted bin root node to those Tcache list heads. And this means that we can get it returned in a subsequent Malloc request. This helps us because the unsorted bin, unlike the Tcache management struct, is not inlined in our heap like the Tcache management struct, but instead it's part of the main arena, or part of the arena, which is stored in GLibc's own virtual address space, and assuming that this is the main arena. At this point, we can make an allocation corresponding to the list head where we wrote that libc address. And so here we requested a chunk of memory whose address was stored in our variable libc pointer. And as you'll notice, libc pointer is a pointer into the main arena. So once we have this arena pointer, we could do a few things. We could read from the pointers surrounding this chunk, and then we could use them to work out the offset to the ROP gadget. We could launch a House of 4 style attack by overriding the least significant byte of the libc pointer to overlap the main arena field, which points to where the top of the heap is. Overriding this, we would ensure that a future allocation is serviced at a controlled address, so the heap will grow beyond its ordinary boundary to overlap other parts of memory. So here we set the top of the heap just to a stack address. And on a subsequent request to Malloc, we might be able to get our chunk to overlap the current stack frame. And from there, we'd be able to overwrite the return address without mangling the stack canary. So here's our memory view. And as you can see here, top was overridden. We could probably have just written our stack address to the Tcache list head directly, but setting a new top ensures that every future allocation will be made relative to that address. So we have a bit of wiggle room and trial and error. I also included this just to emphasize the level of complexity that goes into dynamic memory management and how it exposes different entries of attack. As for a Libsy leak itself, we could achieve this by targeting the input-output management structures, which was used in C4E's House of Rust blog post. And this is where we get a chunk allocated from the appropriate Tcache bin. With a bit of trial and error, we can get it to overlap the standard out GLibc IO management structure. And then after that, we'll overwrite the flags field with this hex value, and then we'll null out those following fields. And from there, we'd hopefully get a huge dump from memory once our process uses the standard out file stream. Then we'll just work out the libc base address and then the relative address of our ROP gadget, and this should hopefully allow us to gain code execution in the end. I've spoken with Allocator, who created safe linking, and we wrote a blog post together about the technique before GLibc 2.32 was officially released. Allocator was really helpful in putting the details of the attack in clear terms, and I appreciate the interest and openness. Additionally, Allocator states at the bypass that it will be a known gap in safe linking's protection and will be a bypass that might be exploited by attackers. So there are a few corner cases which need to be fulfilled, and in this way I wouldn't say that safe linking is broken. It manages to mitigate against many examples of list poisoning attacks. The main purpose of presenting this technique today was to add something to the arsenal and also to point out some of the design decisions in Malloc. Safe linking, in my opinion, is a great mitigation, and props to CPR for its simplicity. I also recommend reading the House of Rust blog post by C4E because it's awesome and presents another way to attack the list heads by using the Tcache stashing mechanism, matching different constraints. So here's some open problems as well. The technique presented here, it aims at bypassing safe linking within the constraints set by CPR's threat model. And to this end, it does succeed, but there are also additional application-specific constraints which also need to be satisfied for this to work. I haven't had much time to explore it further, so I just want to give some additional problems whose solution might further ease the restrictions on Tcache list head poisoning. So one, the question is, can we use the Tcache key as a prev pointer in one of those doubly linked lists? And two, can we take advantage of the consolidation mechanism to consolidate with the Tcache management structure? So in summary, today we kind of covered the basics of memory allocation. So that was automatic, dynamic, and static. Then we looked at exploiting Malloc, and then some historical attacks, so the unlinking, and then the House of Star, and then also double freeze and use after freeze, as well as their mitigations. Then how to bypass these mitigations, and lastly, bypassing safe linking in GLibc 2.32. So my final shout-outs are to Kylie, Silvio, and others such as like Paul and Peter for organising BSides, Faith and Josh for proofreading the slides, and everyone here for listening. Thanks.
Thank you, Jayden, for that talk. Some questions. If you want to ask a question, please go onto the Slack and ask some questions. I suppose I'll start off just by asking, are there any distros at the moment that are using GLibc 2.32? Because I don't think most of the main distros have actually started to use GLibc 2.32.
I have like a Vagrant Fedora box which uses GLibc 2.32, but I think that just might just be like a custom distro rather than like an official release, but I'm not sure.
So when do you think distros will start to use, when do you think Ubuntu might start to use GLibc 2.32?
I honestly, I have no idea, but maybe next year, I don't know.
Well, that's good, that's great. I'll check the Slack if we have any more questions. But thanks once again for a great talk.